Good afternoon, everyone. My name is Sumit Kumar. I am here to take the class on the soil mechanics and geotechnical engineering 1, which is taught by the Professor Dilip Kumar Ved from the IIT Kharagpur. I am working as a PhD research scholar at Department of Civil Engineering at IIT Dhanbad. This coursework deals with the basic concepts of soil mechanics. In the previous two classes, we have understood the particle size distributions, soil classifications, and many more things. The question related to same is also elaborated and discussed. I hope that those concepts helps you in solving your assignment. Apart from that, the content which I have taught, like this PPTs, is also shared with you through Google Drive link, which is shared with you by the NPTEL team. In addition to that, these lectures which I am giving for the 2 hour from 3 to 5 is also get recorded and get uploaded on the YouTube channel. The link for the same is shared with you through the NPTEL team. And apart from that, I also want to add some instructions like this class gets run for 2 hours. In between, we may take the break of 5 minutes, but it will not disconnect the. Please don't leave the meeting. Stay over there. We might take the 5 minute break as per requirement. If it get hectic, we will take a break of 5 minutes. Otherwise, you will continue for the 2 hours. In addition to that, if due to certain reason, maybe network issue, if my call get disconnected, please we remain in the meeting. I will rejoin and continue from there on. Okay. So with this, I will start the today class. Today we are going to study about the permeability and seepage. But as I see that very less people are there in the meeting at this point of time, so I quickly revise the things what we have read, just the key points which we have understood during the previous two class in a very quick manner. In the meanwhile, the other people may get joined. Okay, so in the very first class, we have started with the origin of soil index property and the soil classification, in which we have understood that the soil is the building block. It is used from the basic. It is used as a basic construction material. Apart from that, due to the construction for the construction of any superstructures like building, maybe road, bridges, or the railway embankment, everywhere the soil is the integral part. All the structures which are present across the world are established on the soil one. So we have understood about the topsoil, organic soil, and subsoils. These are the pictorial representation which we have discussed in detail. In addition to that, we have understood that the geologists classify all the earth crust as rock. It might be hard or soft deposit. And subsequently, we understood the rock cycle, in which we came across the igneous rock, residual rock, metamorphic rock, and the sedimentary rock. How their formations, how their property, primarily the igneous, sedimentary, and metamorphic, is discussed in detail. Their property examples and their textures through which we can identify them is also elaborated in very detail. In the sedimentary rocks, what do we mean by strata and how the property get varied is elaborated. Their examples and their brief descriptions get explained in the very first classes. Same for the metamorphic rock. Afterwards, we have classify the rock or on the basis of their formation, in which we came across the transported soil, residual soil, and organic soil. In transported soil, we come across there are the some of the medium which transport the soil from one place to other, in which the water, air, and are the some of the factors which carry the soil particle from one place to the other place for the deposition purpose. Apart from that, the residual soil reside at their parent component only. that is the residual soil, and the organic soil is formed by the decompositions of the natural biological bodies like plants and animals. That is the organic soil, and its strength is also less. How the soil get formed there, based on the particles, like when the flow starts, specifically for the transported soil, the large particle get deposited at the upstream section. Subsequently, the fine particles move in the downward side. This is discussed in the earlier study. Okay, so residual soil and organic soil we have discussed in the very first class. Afterwards, we came across the property like there are the two property due to granular and cohesive soil. One is the two shear strength parameter of soil. One is the friction, and another is cohesion that we have discussed, and how it get formed like the in the granular soil. It is due to the strong interparticular force, but they are loose particle without strong particle forces, while the cohesion soils are made from the particles bound together with the clay materials, right? So that we have understood, the examples is also get discussed, and how they are different from the other engineering material like steel, concrete is also elaborated. Afterwards, the some of the property like the permeability, compressibility, and the shear strength is the some of the characteristics of soil is understood. Then how we identify the soil, whether it is sand, silt, or clay, based on the field identification method is discussed. And then the CV analysis and how percentage final rate get retained, how we classify the soil system is discussed. Okay, so and these are the major things which we have discussed in that class, followed by the week 2 class, in which we have understood the three-phase diagram, in which we have primarily discussed the three-phase system. We understood that in actual, the soil, air, and water, three mediums are present in the soil system. When we idealize it, it get converted into volume of solid and volume of void. Volume of void is filled with either water or air, which make its three phase systems. The various definitions like void ratio, volume of void by volume of solid, porosity, volume of void by total volume is also discussed over there. Then subsequently, the other parameter like GS, gamma, W is also discussed. The main things in the three-phase system is elaborated over here, in which the figure A, it is presented the dry soil in which only the air sorry, only the air is present apart from the soil solids. While in the saturated system, all the air is replaced with the water, so the solid and water is only present. But in actual, in maximum cases, the three-phase system is present, in which the volume of void is filled with the air and water only, that is said to be the partially saturated soil. Then the degree of saturation we have defined, in which we have said that the volume of water by volume of void, how much the volume of void is occupied by volume of water, each represent the degree of saturation. And then the density unit. This is the basic thing which we have discussed it very deeply during that class. Moving ahead, we understood the several correlations, which I think so you must be aware of. Afterwards, we have solved some numerical problem in which we calculated the water content, void ratio, and degree of saturations. Then these problems we have discussed, like how the volume of solid and the weight of solid remain constant, because that doesn't change irrespective of the places where we have to kept. And this is the basic relations which I have defined, that the volume of solid is equal to total volume by 1 plus E. So similarly, W is equal to WT by 1 plus sorry, a little bit cough I have, so that's why it is a problem. That's why I have tried to start little early, so that I can cover entire thing in the given duration. Okay, no problem. So these problems we have discussed, I can skip the problem because we have discussed those in detail. Uh, After that, we came to the permeability and seepage. Um, Today we are going to solve the many problems related to uh, many numerical problems which we have read in the earlier classes as well. Okay, I'm sorry. Okay, so in these things which we have understood in the previous classes, so I think so now I can go ahead with the new content. These are the basic things which we have understood in the previous classes, like the adhesion zone, saturation zone, rock flow zone. In addition to that, we have understood about uh, the liquid limit, plastic limit, natural water content. We also classified the soil on the basis of that only. So then the consistency limit and liquid limit is also discussed during those classes. So these are the major things which we have came across in the previous class. Now I think we can move ahead with the new content. Okay, you see that this permeability and seepage concept which we have discussed for the unconfined aquifer, and subsequently for the confined aquifer which we are going to use it over here in the present class. Okay, so let me move with the new content and solve some problems related to sin. So in today class I discuss the theory very briefly, and sorry, sorry, give me a minute. Okay, sorry, let me start again. Okay, so I think so now I can start with the new content. It's also get the time so that new content discussion could be started from this point of time, so that those who want to join could be there, right? Okay, so let me start with the new concepts, new contents. Okay, so today we are going to discuss about the permeability and seepage. So first of all, understand the permeability and subsequently seepage. So in the previous class, if you remember, we have discussed about the permeability, where we came across the terms like uh, I have sorry, I have given an example like let me take a pen and draw it for once, in which I have said that take a container, first of all fill it with gravel and make a perforation from here to flow out the water from the bottom cells. As you see, when you keep the coarse particles, large blocks, when you keep the large blocks over here, the flow of water takes place at the different rate. Okay. Subsequently, you take the same container and take relatively small size particles, and they are kept side by side. As I draw this much gap, this may not be there as we keep the small size particles, and then you allow the flow of water from there only. So you find that the amount of water goes down in a specific interval of time from this and from that is at the different rate. So as the more voids is present when the large size particles are present in the same container, the water flow from that section is at the relatively higher rate, which is not with the other container in which the fine size particles is there. Okay, so this is the basic difference. Over here the coarse size particle is there, and over here the fine size particle is there. Just for example, when we go in detail, we see that gravel have the highest permeability. We also see the rate of permeability, the range of permeability in general for the gravel, sand, silt, and clay. So we find so we found that in the gravel, the rate of flow of water from the through the particle is very high. Give me a minute, please. Okay, so let me continue. Actually, I have little bit cough and fever, so today's class may be interrupted little bit. So excuse me for that. And I also try to finish it a little early if possible, if the everything is get covered. So please excuse me for that. Okay, let me continue. Okay, so I am discussing about the permeability. So I have explained this term that how the permeability is highest for the coarse particles. Coarse particle like gravel have a highest permeability, followed by sand, followed by silt, and followed by clay. And this range is the what is the range of permeability also discussed in the previous class. And the PDF which is shared with you have that range. So the rough idea you need to have, not on size, but you need to understand, because some problems, if some MCQ question get framed, maybe in your assignment or the exam which get conducted at the end of the sessions, this type of problem is there. In addition, sorry. In addition to that, if you are going to give the some of the examination like GATE or engineering services, the problem related to the permeability may be asked over there, that what is the rate of permeability, how whether the sand is more permeable or the gravel. In addition to that, as we move ahead, we see talk about the settlement. Over there we see that okay, when it comes we will discuss. So these are the things. Now over moving ahead, we have developed the equation of flow through soil. So over here you see that we have taken a small amount of soil which is at height h from the surface, below the surface, and we develop the equation. So first of all, you understand the simple concept, that is the component of hydraulic gradient. Hydraulic gradient is nothing but head loss per unit length. Okay, so over here you see the component of hydraulic gradient Ix at the center of the element will be curl h upon curl x. As you see, over here, h is that distance, h is the loss of head takes place between that element, and x is the distance through which the water flow out. So over here, negative signs is there because the head loss in the direction of. Okay, let me give you example. You see that you have maybe read the open channel flow or find fluid mechanics. Over here you see that when the flow takes place, maybe over here if we have pressure tube, piezometer. Okay, so here may be some head, and this is the head of water, right? And over here, head of water get reduced as the water move downstream, right? So as we move in the direction, assume this is the x direction, and this is the h1, and this is the h2, and this is h1. Okay, so from h1 to h2, as we move in the direction of x, the h1 minus h2 is the head loss, but this head get reduced as we move in the positive x. Hence, to keep the overall thing positive, we put a negative sign. It is also written over here that it is of negative sign as there is a head loss in the direction of flow. At the upstream section, as the flow started over there, the head is more, but as it move ahead, head get reduced. The when we put the piezometer over here, the water table in that piezometer is less as compared to the upstream section. Subsequently, when we go ahead and talk about the rate of change of hydraulic gradient Ix along the length of the element in the x direction, then we write as curl Ix by curl x square. So how we write it? We write it as curl Ix by curl x. So this become curl by x of curl h upon curl x. And this ultimately turned into curl square h by curl x square. I think so this thing is understood. Now, hence, the gradient at the face of the element nearest to the origin become minus curl h by curl by curl x plus curl ix by curl x uh, multiplied by minus dx by 2. Hence, from this we have make the component in the 3 dimension. Basically, as per Darcy law, you know, Darcy say that from the Darcy law we know that Q equal to KIA. Q equal to KIA, and when we say Q equal to KIA, over here Q is the discharge in meter cube per second. If we keep everything in SI unit, so it is a discharge in meter cube per second. K is the permeability in meter per second, And I is nothing but hydraulic gradient. It is head loss per unit length, delta H upon length, L or Lx, whatever you say, or X, and A is the area of cross section in meter square. So this is the basic thing, and this Darcy law is valid in the constant head permeability test. What is the constant head permeability test we see? And and the question, the problems, numericals, which could be solved on the basis of that will also be discussed ahead. So we use this equation, and we ultimately find, basically over here you can see that A is written as dy dz, K is written as kx, and I is written as curl h by curl x, and in the other direction it is converted to, this term is only curl square h by curl x square into dx by. So this is written, and then we uh, gradient at the face farthest from origin. So we apply some boundary conditions, and we, but this is not important. The main thing is q equal to kia, and we use these equations only, that is q equal to kia, for calculations of the discharge or maybe permeability at some point of time, when we know the what is the amount of head loss, how the amount of head loss is detected by using the piezometer, or maybe piezometer only, that what is the head loss takes place between the section 1 and 2. On the basis of that, we found the net change in the head between the two specific point, maybe 1 or 2, and on the basis of that we are able to calculate the discharge through those two cross sections. And the permeability, like kx, ky, kz, maybe vary also in other two directions like y and z. Then the k equivalent could also be found as kx into ky into kz up to the power 1 by 3. So this is that is the give me a minute please. Okay. Okay, so I am talking about the permeability and seepage analysis. So we have understood that q equal to kia, and how the volume 1 and 2 takes place in the different direction. K, ky, kz could be different, could be same, but in general, we in the three-dimensional flow, we assume soil as isotropic. If soil is isotropic, hence it has kx, ky, kz same, because same property in all directions. Hence kx, ky, kz is same. Sorry. Okay. So those are the things only which are over here. Now understood the two important term. One is phi and another is psi. Basically, equipotential line and flow line. There is the two different things. As we go ahead, we come to know across some term like Q equal to K KH into NF by ND, like this. Okay, let me raise this at this point of time. I will show you once it's that concept came. So you need to understand that what is the flow line and what is the equipotential line. So if you see, um, at certain condition, if water table is there in the upstream side up to this level, or in the downstream side up to this level, the water flow takes place from this section to that sections. So this is the flow lines through which the flow takes place from, if the water level is more up over here, um, if the water table is more at this level and over here the water level is less, so it is obvious that the flow takes place in this direction. Okay, so this is said to be the flow line, and perpendicular to this direction is the equipotential line. So um, basically, perpendicular to this, uh, we draw the equipotential lines, right? I will elaborate with some more figures as well, but this is the basic things which are there. So over here, the Laplace equation is presented for the two conjugate functions phi and psi. Over here, ux, vx, dx is nothing but velocity in x direction. Is curl phi by curl x, that is equal to k into ix, and ix is nothing but curl h by curl x, so it is minus k into curl h by curl x. And when talk about in the vz direction, it is curl phi by curl z, and then that is ki, v equal to ki from the Darcy law. Q from Darcy law, q equal to kia, q equal to kia. When we divide q upon a, it become v, and it become ki. Okay, so this is ki, and I is head loss per unit length. When we move in the x direction, it is curl x. When we move in the z direction, it is vz. Okay, so the kiz also, so curl h upon curl z. And then curl square phi upon curl x square become k minus k curl square h by curl x square. From this one, over here you can see, from this condition only, right? So similarly for the z direction also, when we sum them, curl square phi this become the Laplace equation, and these equations the equations which we form the Laplace equation for the permeability and seepage. Now move to the flow line and equipotential line. As I have drawn over here, you can see this is the flow line and this is equipotential line. Okay, so first of all, I read the definition and then move ahead with in detail for those concepts, and then solve some problems. When we go to the problems, you will understand the differences. Okay, so the flow line, the path which water particles follow in course of seepage are known as the flow lines. Water flow from point of the high to the low head, as I have shown over there in that figure. I will go ahead and makes smooth curves when changing directions. Hence, one can draw the series of smooth curves representing the path followed by moving particles. Okay, so basically, when we talk about the flow lines, the एक स्पेस okay. When we talk about the flow line, specific particles follow this path only while moving from this end, this upstream side to the this lower stream side. When we catch one particle and follow its path, it go from that direction only. Subsequently the second particle, it doesn't mean that no flow takes place from this place, no flow takes place at this point of time. When we draw some other flow line and equipotential drop line and we calculate kh into nf by nd, for the discharge takes place, uh, over there we will discuss more elaborately that, but in general, if I draw this flow line, a specific particles uh, flow from this path only. And when we talk about the equipotential line, so the head at this sorry. Okay. Okay. So, again, I will read the flow line and then the equipotential line. And I have explained the flow line. Equipotential line is also as I have drawn in the perpendicular direction. So, again for the flow line, the path which water particles follow in the course of seepage are known as the flow line. Water flow from point of high to low head and make smooth curve when changing direction. Hence, one can draw a series of smooth curves representing the path followed by moving water particles. When we talk about the equipotential line, as the water moves along the flow line, it experiences a continuous loss of head. If we can obtain the head causing flow at a point along the flow line, then by joining up the points of equal potentials, one can obtain the second set of lines that is known as equipotential line. Okay, when we talk about the equal potential, over here one thing is written, if you have interestingly seen, joining the point of equal potential, one can obtain the second set of line, that is the equipotential line. Okay, so when we have drawn the equipotential line, over here you can see that the you can see that the head at all these points remain same. Okay, so that's why this equipotential line get developed, because at some point of time the head at the different section remain similar, so that result in the formation of the equipotential lines. Okay. Okay. Now we talk about the flow nets. The flow nets is the flow of water through the soil, can be represented graphically by the flow net, a form of curvilinear net made up of the flow lines intersected by equipotential lines. That is the point joining the equal head points, right? So over here you can see that the flow net is developed. Okay, as I have drawn earlier picture, you have seen over here, then the similar picture is drawn. Now I will use the laser point to elaborate this, that you see that this is the flow line. As I move the laser from this point to this is the flow line, this is the flow line. From the in this direction the flow takes place. Similarly, this is the equipotential line. At this line, the pressure head remain constant. So these are the equipotential line, which we have discussed in the previous slide. And this is the flow channel through which the flow takes place. So the over here again you see it is mentioned separately also, that this is the flow line, this is the flow line. The channel between the flow lines is said to be flow channels, and these are the lines at which the potential, that is the pressure is head is same, so that is the equipotential lines, right? And this is the flow channel through which the flow takes place. Now, now when we see the figure, so a typical flow net representing seepage through the soil beneath a dam, right? And that's why in the upstream side the head is high, so the flow takes place from upstream height head to the downstream head. The flow is assumed to be two-dimensional from Darcy law, Q equal to KIA. We already know that A KI is nothing but KIA. K is the permeability, I is the hydraulic gradient, A is the area of cross section, Q is the discharge. So we can consider unit width of the soil. If delta Q equal to unit flow through the flow channel, then delta Q equal to K into B into 1, because unit width, and into I. So this become K into B into I, where B is the distance between the two flow lines. Okay. In figure, you can see that A, B, C, D has been mentioned over here. So is bounded by the same flow lines A1, B1, C1, D1, and by the same equipotential as A2, B2, C2, D2. Okay, A1, B1, C1, D1, right? And potential drop is A2, B2, C2, D2. Okay. For any figure in the net, delta Q is given as K into delta H by L into B. KIA nothing. Delta H by L is I, and B into 1 is the area. B into 1 is area. So this is KIA, Darcy law only, right? Where delta is the head loss between the two equipotentials, and L is the distance between the equipotentials. Now, for the flow through A1, B1, C1, D1, delta Q1 equal to K into delta H1 by L1 into B1 into 1. For A2, B2, C2, D2, it become delta H2 by L2 into B2 into 1. So in general, what we can write, K into delta H by L into B. So if it is possible to draw the flow net so that L1 equal to B1, L2 equal to B2, and L equal to B, when we have the arrangement in the figure termed as the squares. Okay, if these arrangements at this point of time is not squares, but if arrangement are squares, then over here you see L, this direction, the flow direction is L mentioned, and the weight direction is B is mentioned. So if it is a square, then L equal to B, right? So if L1 equal to B1, L2 equal to B2, then L equal to B. When we have this arrangement in the figure, are termed as a square, and the flow net is a square into flow net, with the condition as B1 by L1 equal to B2 by L2 equal to B by L. Okay. Okay. So if it is a square ABCD, then delta Q equal to delta Q1, and since ABCD has a same equipotential as A2, B2, C2, so delta Q is also equal to delta Q1, and if delta Q equal to delta Q1, then it is also equal to delta Q2 for any other square cross sections. And So the head loss between those subsequents 1, 2, and delta H is also same. Okay, so now we generalize it in the term of number of flow line and number of equipotential drop. Hence, we can assume that H is the total head loss takes place. Uh, so over here, head is this. In downstream side, head is this. Then the loss of head takes place between these two each. This is delta H. So, if H is the total head loss and Q is the quantity of flow unit, so delta H is H by ND. Okay. And delta Q equal to NQ by NF. Basically, when we talk about delta H equal to H by ND, we say that all, if it is a square, all head loss takes place as we have elaborated over here. L1 equal to B1, L2 equal to B2, L equal to B. In that case, if we have considered it as a square, then the head loss takes place between two drops, which also going to be same. Like if you can see, I draw this line and this line, and this is potential lines. Okay, so the head drop, head loss takes between this line and this line, 1 and 2, each same as 2 and 3. So head loss takes place, if total head loss takes place is H, right? Then head loss takes place in one section each H by ND. How much drop? If over here 1, 2, 3, 4 drop, then it is H by 4, right? So that is delta H equal to H by ND. See, in the same case, the total flow quantity is Q, then the number of flow lines over here 1, 2. So delta Q equal to Q by NF, where NF and ND are the number of flow line and the potential drop respectively. So combining all these, this become delta H equal to H into delta H by B by L equal to K into delta H. B equal to L for the square flow. So so um, so this become delta Q equal to T into delta H, and subsequently K into H by ND equal to Q by NF. So these equations get developed: Q equal to KH NF by ND, where H is the head, K is the permeability, NF is the number of flow lines, and D is the number of drop takes place. And on the basis of this, we can calculate the amount of discharge takes place per unit length. Per unit length. This is also important. Discharge per unit meter, per meter, per meter length. Okay, because we have assumed over here delta Q equal to K into B into 1. This one is unit width. We have assumed unit width. That's why the Q is calculated per unit length. Okay. Now, again, we have shown problem. Okay, so from this figure, you can see Okay, allow me to take a 5-minute break. Then I continue. I will start from 3:40 or 3:40. 5-minute break is there. In a meanwhile, a very small problem I have opened on the screen. Please try to solve it. Uh, I start with solution of that problem. Then we go backward and again start the concept. I have already taught that topic. That is based on Q equal to KIA, Darcy law only, constant head test, in which you have to calculate Q equal to KIA. Everything is given. I think so. Answer is also written, so you can calculate. So over here you have 5 minutes to solve that problem. I hope that everyone could able to do so. A very easy problem. In 1 minute time you can solve. Okay, so after 5 minutes I will start speaking because I'm not really comfortable in speaking. So excuse me for that. Okay, welcome back. Okay, so I've asked you to solve this problem. So this question is very simple. This is solved on the basis of the basic concept, that is Q equal to KIA, which we have discussed as well. So over here, it is given that the result of constant head permeability test in a fine sand are as follow. The area of sample is 180 square centimeter. The length of the specimen is 32 cm. And the constant head is maintained 46 cm. The flow of water through the specimen is 200 ml in 5 minutes. To determine the coefficient of permeability in cm per second. So I have solved this problem for you. The Q discharge is given as 200 ml per 5 minutes. So Q is given 200 ml by 5, and K we have need to calculate, and I is also given as the constant head is maintained of 46 cm, and the length of the specimen is 32 cm. So 46 by 32 is hydraulic gradient for this question, and 180 square centimeter is the area. So if you put all these things, you could able to solve this problem very easily. And let's see the solution, which I have already done for you. So over here, as it is mentioned, that area is 180 centimeter square, length is 32 cm, and constant head of 46 cm is meant. So first of all, I have calculated the discharge in cm cube per second. So this is Q is 200 ml per 5 minutes. So 200 by 5 cm cube per minute, because ml is centimeter cube. Okay. So this subsequently become for 200 by 5. If we did 40 centimeter cube per minute, but I want to convert it in cm cube per second, so I also divide it by 60, so it is 2 by 3 cm cube per second. And now for the constant head permeability test, Q equal to KIA. Q equal to KIA is used, which I have already told to you. So we have used Q equal to KIA, and K need to be calculated. I is head loss per unit length. Head maintained is 46, which is already mentioned over here, 46 centimeter, 46 upon 32. Into area of cross section is 180 cm square. So we are going to get K in the cm per second. So K equal to 2.58 into 10 to the power minus 3 cm per second, which is 0.00258, which is also already mentioned over here. I hope if you have tried this at this point of time also, you could you have easily solve this problem. So this much is the problem which you need to solve in this 5-minute gap, but I don't know whether you tried or not, but I suggest that must try the problems to solve. If you don't try the problems get solved by yourself, the learning remain inadequate. Okay, so where I am before. Okay, I am here before we have take a small break. So let me continue from here. Okay, so whether my audio is on or not. I'm audible, na? Hello, am I audible? Anyone can reply. Hello, hello, Sadiq.
Yes, sir, you are audible, sir.
Okay, okay. Okay, so we are here. We have just understood that KHNF by ND, and over here our problem has been given in which just for example, not any questions over here. In figure A, you can see that dam type structures get created, and you can see that the seat pile of 5 meter is also used in the downstream side. The length of the width of the dam is 25 meter, and we usually calculate the discharge per unit length. for this section, because we have calculated assumed B into 1 as area, because the depth in the direction of the screen, depth in the direction of screen we have considered as 1. And in the B you have C the boundary conditions, like equipotentials is shown over here for this type of conditions. In step A, we draw the flow line. The flow line is visible. In next step, we draw the potential equipotential line. Equipotential line is drawn with the help of the piezometer. We find that how much head is there at each line where the head is equal. We join those points and get from the equipotential lines. Subsequently, the overall flow net get developed, in which these lines show the flow line through which the flow takes place, and these lines are show the equipotential line at which the drop is constant. We have joined the constant drop lines, we have joined the flow points, and the overall flow net get formed. Right now, we move ahead, and we see that the most loose deposits are probably isotropic. That is, the value of permeability in the horizontal is same in the vertical direction. The particle of construction of the earth dam, earth embankments and dams is spreading of soil in the loose layers and then compacted. These construction techniques result in a great value of permeability in the horizontal direction, then that in the vertical direction. The value of vertical direction usually 1 by 5 to the 1 by 10 of the value in the horizontal direction. Okay, so that could also vary, also we have already discussed. And the general difference in the equation for the flow in the three-dimensional case we are derived earlier, we have already derived, where we have written h kx into curl square h by curl x square plus ky into curl square h by curl y square plus kz into curl square h upon curl z square equal to 0. Similarly, for the two-dimensional, the curl square h upon curl x square and the curl square h upon curl z square remain over there. And to transform these equations is also sometimes used, in which okay. Mhm. Okay, so I'm telling about that the unless the kx is equal to kz, the equation is not a true Laplacian and cannot therefore be solved by the flow net described before, because in the previous equation in which we have used kh nf by nd to calculate discharge, where k is the permeability, h is the head difference between the upstream and the downstream, nf is the number of flow lines, and nt is the number of equipotential drops. So if that is not sorry that could not be the used if the permeability in the horizontal and vertical direction is not same, because the isotropic soil condition is assumed for those cases discussions. So to utilize that method only, some modification could be made for an equivalent homogeneous systems. For that, we used this equation only. This equation is only important. Over here, its derivation has been written, but this equation is only important to transfer x to xt if kz and kx is not same. If the permeability in both direction are same, then xt equal to x only. Okay, if transformation is needed, then we do xt equal to x into kz upon kx root under, right? And the equation modified is now a Laplacian and involves the two coordinates variable xt, x subscript t, and z, and it can be solved by the flow net, provided that the net is drawn to a vertical scale of z and a horizontal scale of xt equal to x into root under kz upon kx, where kz and kx is the permeability in the z and x direction respectively. Now you see from this figure that the seepage quantity in the anisotropic soil head loss is painted as delta H. Over here in the figure A, you can see this width is A. For the transformed width, it converted into A into root under kx upon kz, because we have to calculate A transformed. Over here equation is xt equal to x into kz by kx. So we need to calculate this x. We need to calculate this x. So this become xt into kx upon kz. So kx upon kz into A is the transformed boundary. Similarly, for the A, and the transformed and original boundary is presented. So this equation remains same as q equal to kh into nf by nd. Just the value of transformation get changed. So the only problem is that what is the value of k is used. So if k is same for both the cases, there is no problem. It is different, then we use these conditions. Now, one of the most important concept is the k equivalent. Okay, so if the permeability in the x and q, even when we use the simple equation of q equal to kia, over there also we assume as isotropic condition. If it is not isotropic case, then the permeability value get vary in the different direction, then we have to calculate the equivalent permeability. So using the transformed scale of square flow net is drawn, and NF and ND are obtained. If we consider a square in the transformed flow net, it will be shown in figure A. The same figure drawn to the natural scale, that is x, scale x equal to scale z, will appear as shown figure B. Let Ke be the effective permeability of the anisotropic condition from figure A. Q equal to A Ke into delta H by A equal to Ke into delta H. And then again Q from figure B, okay, from figure A, A into K into delta H upon A, बिल्कुल. So A and A get cancelled, so K into delta H. From figure B, A into Kx into delta H by A into Kx by Kz. So this become A and A get cancelled out. So and Kx become root Kx and root Kx into root H. So this over here K equivalent become Kx into Kz root under. So this is presented over there, right? So this becomes again different thing is also there over here. Only two direction. If k is varied in the three-dimensional space and kx, ky, kz is there, then K equivalent is not root under Kx, Ky, Kz. It becomes Kx Ky Kz to the power 1 by 3. Okay. So this is also equally important. Sometimes this question, not the problem based on this problem, but K equivalent for the 3 direction is also came, and option is given as K, Ky, Kz root under, and many people think that K equivalent equal root under Kx, Kz, so it is also Kx, Ky, Kz, but that's not the case. If it is in the 3 dimensional, the K equivalent become Kx into Ky into Kz to the power 1 upon 3, right? Now you see, now we talk about the critical hydraulic gradient. Okay, critical hydraulic gradient is that section at which the basically total effective stress equal to core water pressure. Okay, sorry, effective stress, total stress equal to total stress core water pressure. Okay, so I think so I have said something wrong. Let me rethink. First of all, read the critical hydraulic gradient. So the total head of water above the base, over here you can see from this figure as small h plus capital H plus L, and the head of water in the sample above the base is H plus L. Therefore, the excess hydrostatic head is gamma W into H. Exactly, no problem. Now, if any friction between the soil and the side of the container is ignored, then soil is on the point of being washed out when the downward force is equal to the upward forces. Okay, so downward force is equal to buoyant unit weight into volume. So equal to gamma W into G minus 1 by 1 plus E into A into L. Upward force equal to H into gamma W into A. Gamma W cancelled. A and A get cancelled. And H equal to H by L equal to G minus 1 upon 1 plus E. So hydraulic gradient equation get converted into I. Critical hydraulic gradient is IC equal to GS minus 1 plus E. Okay. So this is the basic condition which get developed. Right. Now we move to the problem. Okay. So we have approximately 6 or 7 problems which we first of all discuss before moving ahead. After discussing these problems, some of the techniques, destructive and destructive techniques which we used to for the soil to get in the good conditions before the construction work we are going to discuss. So first of all, start with this problem. Okay. So first of all, I read the problem, then followed by the solution, which I already kept in the subsequent slide. We will discuss one by one. Okay. So first question say that a large size excavation is made, and remember this question is also taught by these concepts are taught by sir, but is not discussed in and the solution is not presented over there. So I am going to give the solution for that over here. So a large size excavation is made in a stiff clay whose saturated unit weight is 17.27. So the gamma sat is 17.27. Given what is the given and what is being asked, you need to understand while reading the question only. Okay. When the depth of excavation reaches the 7.5 meter, the crack appears and the water begins to flow upward to bring up the sand to the surface. Okay. When we are doing excavation and depth of excavation reaches to the 7.5 meter, crack appear and the water begin to flow upward from that section. Subsequent boring indicate that the clay is underlain by the sand at the depth of 11 meter below the original ground surface. So what is the depth of water table outside the excavation below the original ground level? So what is the depth of water table outside the excavation? जहाँ excavation कर रहे हैं उसके outside में what is the depth of water table below the original ground level? So over here you can see I have mentioned everything that the saturated unit weight given 17.27. Depth of excavation is 7.5 meter. Okay. Then the crack and the boiling sand plus water appear at the 7.5 meter, indicate that the peeping or the heap due to the upward seepage pressure. So clay, and apart from that, additional condition is given that clay is underlain by the sand at the depth of 11 meter. Okay. So the thickness of clay is also given as 11 meter, and it's a find what we need to find depth of water table outside the excavation from the original ground surface. Now we know that uplift takes place when the effective stress is equal to pore water pressure. In that case only the uplift, heaving, boiling takes place. So uh, 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 in this condition the upward seepage pressure overcomes the effective stress at the clay sand interface. Over here u is the effect pore water pressure while the sigma dash is the effective pressure. Now we apply the principle of effective stress at the bottom of the clay layer. So what we do, we say that the u equal to the pore water pressure at the bottom of the clay from the outside of excavation as gamma w into 11 minus z, where z is assumed to be the depth of water table. Let the depth of water table z meter below the ground surface. Okay, ground surface. So z meter below the ground surface. So pore water pressure is gamma w into 11 minus z only, where gamma w is equal to 9.81. Now inside effective stress at the clay sand interface inside the excavation. Okay, so inside the excavation only 3.5 meter of clay remains above the interface. Since the excavation is 7.5 meter deep and interface is 11 meter depth, so the total stress at the bottom is gamma sat into 3.5. Okay, we are using the we are calculating over here the total stress over the pore water pressure. Since the bottom is exposed and water is flowing up, so effective stress is 0. If effective stress is 0, then total stress equal to pore water pressure, and pore water pressure is gamma w into 11 minus z, and total stress is gamma sat into 3.5. When we calculate, we already know gamma sat as 17.27, gamma w as 9.81. Only z is unknown. When we solve it, we find the z as 4.84 meter. So the answer is 4.84 meter for the depth of water table outside the excavation below the original ground level. Okay, very simple. I share this PDF. You go across this problem by yourself, solve by your hand, and afterwards we can come to the solutions. Okay. And in addition to that, I also suggest that you can take any book, any basic soil mechanics book, whichever is available with you. Maybe Gopal Ranjan Rao, or many books are there which are available in the library, or if you are a student, a college going student, some of the books PDF is also available on the internet. Also, when you search on Google, some are the openly available. So you can download PDFs also if not have the soft copy, and try to solve the problems related to the permeability and seepage before coming to the next class. So your concept gets strengthened, your practice get better, and you could able to answer the problems, any type of problem in any examination, or maybe the competitive exam which you may going to have. Okay. So now I move to this problem. This problem say if the excavation is carried out in a soil with the porosity is 0.40. I think you remember porosity is volume of void by total volume, uh, and it is represented by N, and the specific gravity G of solid is 2.65, GS is 2.65. It is given. Determine the critical gradient. If you remember, the equation for the critical gradient as IC equal to GS minus 1 by 1 plus E. It is read by you today only, GS minus 1 on 1 plus E. Over here in this question, you know the value of GS as 2.65. You don't know the value of E, but you know the value of N. N as 0.40. In the previous class, we have understood a relation to calculate the void ratio from E equal to N upon 1 minus N. Okay, so you use this equation, E equal to N upon 1 minus N. You calculate the E. Once you calculate the everything is known to you, you could calculate the critical hydraulic gradient. Okay, so this part of the problem is solved. Now again it's a 1.5 meter layer of soil is subjected to the upward seepage head of 1.95 meter. Okay, so what depth of coarse sand would be required above the soil to provide the factor of safety of 2.5? Assume that the sand has same porosity and a specific gravity of solids as the soil. Okay, so that's not the problem, and this is also a very simple problem. So first of all, we see the solution for IC, and then I have also written the solution for the second part of the problem, in which the request factor of safety 2.5 is achieved by putting what much depth of sand above that. This is a similar problem related to the previous questions, so that's not the difficulty. Okay, so first of all, you see, as I have said, IC equal to GS minus 1 by 1 by plus E, and E equal to N by 1 minus N. So we calculated the N, and then we calculated the IC, which is found to be 0.99. So it is almost in the critical condition, because critical hydraulic gradient is 1, so it is a critical. So it is very close to 1 and below 1 only. So it is in the critical condition. Now the actual upward gradient through the soil is H upon H soil, as it is written that the head of 1.95 meter water and the height of soil is 1.5. So I actually is 1.3. So if this is greater than IC is 0.99 and this is 1.3, so the soil is at the risk of peeping or heaving. Okay, because IC by I is the factor of safety. When we calculate factor of safety, now it is I critical by I. So I critical is 0.99 and I is 1.3. So the factor of safety is less than 1 at this point of time, because 0.99 by 1.3 is less than 1. Okay, this is the basic thing. and the factor of safety, okay, I will write over here also. If we found to calculate factor of safety in the term of hydraulic gradient, this is IC upon I. Okay, so this IC upon I is nothing but 0.99 upon 1.3, which is less than 1. So it is at the risk of keeping or heat. So to reduce the risk, we must reduce the gradient acting on the soil. So we do this by adding the sand layer above the soil to absorb part of head loss. So first of all, let the required thickness of flow pass sand plus soil equal to H total equal to the required gradient to get the factor of safety 2. I already say IC by I level equal to F4 FS, because I in the previous slide I have said now factor of safety equal to IC by I. So required factor of safety is 2.5. So I level equal to IC by factor of safety. So I level is 0.396. Now I total equal to H. H is already fixed, that is 1.95 meter, and H soil is known to us as 1.5 meter. So H sand we need to calculate. So we use I total equal to H by H sand plus H soil equal to 0.396. H is known to us, H soil is known to us, H sand is considered as X, and that value is 3.424 meter by solving this. I think so. This is very much clear for everyone. I think so. Okay. So please read this question again and try to understood. If you have any doubt, let me know. Okay. Okay. So I think so. This is understood by everyone. So let me move to the next one. Not to cover before 17. Okay. Let me go a little fast. Maybe I will solve a numerical problem in this manner only, very essentially. For the theoretical concept, I can go ahead because that's you already understood with the sir class only. So the numerical are solutions are not there. So I feel this solution helped you a lot. Okay, so this question we already solved after the start at the start of the break. So I move to the next one. Okay, now you see over here. There are the various tests to calculate the permeability, like the constant head, falling head. So over here, this question is based upon the falling head test. Question say, compute the coefficient of permeability of soil on which the falling head test has been carried out, in which it is given that the area of sample as 80 centimeters square, area of the standpipe as 4 centimeters square, the length of the soil sample as 15 cm, and the time versus the head difference reading is given at time at 0. Head difference is 107, and for 27 minutes it is 105, and 60 it is 103. Again, the given point is A equal to 80 centimeters square, standpipe area small area presented 4 cm square, length of soil sample L as 15 cm. the time versus head difference data is also presented here. Okay, so we will use the 2 point to compute the coefficient of permeability K using the falling head permeability test formula. So K equal to AL by AT ln H1 by H2, where A is the area of standpipe, L is the length of the soil pipe, A is the area of cross section, T is the time interval, H1, H2 is the initial and final heads. Okay, so when we see, first of all, we have calculated K. K is AL upon AT. So small a is 4, length is 15, 4 into 15, that is, and capital A is 80 centimeter square. T is 60 minus 0, basically 60 minutes, multiplied by ln 107 by 103, because at t equal to 0, head is 107, at t2 equal to 60, head is 103. So with this, we are going to calculate. So when we solve it, we first of all calculated 4 into 0.15 by 80 into 60 as 0.0125. Then we compute ln 107 by 103 as this. While merging all them, we find K equal to 0.004675 centimeter per minute. When we convert it in cm per second, it is found to be 7.94 into 10 to the power minus 6 centimeter per second. If it is need to be obtained in the meter per second, it is going to be 7.94 into 10 to the power minus 8 meter per second. Right. So this is a simple problem which is based on the falling head permeability test. Now I move to the next questions, which state that for a field permeability test, by pumping out, a well was sunk through a horizontal stratum of sand 15-meter thick and underlain by the impervious layer. Two observation wells were stuck at the horizontal distance of 15-meter and 35-meter, respectively, from the pumping well. The initial position of water level was 2 meters below the ground level, and after a steady state pumping at the rate of 925 liter per meter, the drawdown observed found to be 2.5 meter and 1.3 meter respectively. To calculate the coefficient of permeability. Okay, so over here you can see the this is the question which is based on. Okay, let me take a pen. This is a question which is based on the basis of confined aquifer, because the horizontal stratum of sand of 15 meter thick in which the water is present. So you remember in the previous class we have understood some concepts. Let me show you the PPT. Okay. In the previous class we have understood the confined aquifer. Okay, and we also read about the unconfined aquifer. In the unconfined aquifer, we take the water from the upper layer only, while in the confined aquifer, we take the water which is trapped between the two of the impermeable layer, and from this we excavate the water. Over here, K is calculated as Q into ln R by RW into pi H square minus H naught square, while over here we calculate K as Q ln R 2 by R1 2 pi H H2 minus H1. So in the given problem, it is a confined aquifer, because if you have read the problem, let me read the problem again. If you have read the problem, it is clearly written that the for a field permeability test by the pumping out, a well was sunk through the horizontal stratum of sand 15 meter thick sand stratum, underlain by the impervious layer. Basically, at above impervious layer is there. After that, a sand layer is present in which the water is there. So from there we are excavating water at the rate of 925 liter per minute. So what is the permeability, what is the key value we need to calculate? So we use this equation only, in which okay, in which we are going to use as k equal to q into ln r2 upon r1 by 2 pi h, where h is the 15-meter thick and h2 minus h1 is the head difference. Okay, so over here you see in this is the 2 pi h value. Okay, and r2 is 35, r1 is 15, and 2.5 minus 1.3 each, h2 minus h1. So let's go step by step. I just shown the previous class that concept to remind you that what we have read and from where we are going to solve this problem. Okay, so let me see that in this question it is said that it is given that the thickness of stratum layer as b equal to 15 meter, that is nothing but h, which I have shown in the formula in the previous class. The distance of the observation well R1 and R2 are the 15 and 35 meter respectively. The initial water level is 2 meter below the ground level and the pumping rate is 925 liter per minute, which is converted in meter cube per second. The drawdown is 2.5 and 1.3 at the radius of R1 and R2 respectively. For a confined aquifer, fully penetrating well, steady flow, the K equation is written as this, and when we calculate the value of K, it is found to be 0.000115 meter per second. I think so. There will be no doubt over here. We have used the Q value, which we have already calculated as 0.001542. We have uh, R2 value as R2 by R1 is 35 by 15, that is 2.313, 2 pi b, and b is 15 meter, h2 minus h1 is 1.2 meter. That's what we have used and calculated the value of k. Right. Now I move to the next problem, in which it has been asked that a bed of sand consists of three horizontal layers of equal thickness. The magnitude of coefficient of permeability of both upper and lower layer is 4 into 10 to the power minus 4 mm per second, and for the middle layer 6 into 10 to the power minus 2 meter mm per second. What is the ratio of average permeability of the bed in the horizontal direction and the vertical direction? Okay, so the equation related to same is not discussed earlier, because with this problem only I am going to write the equations. So over here there is the three layer is present of different permeability: the upper layer, middle layer, and the lower layer. So for these two layer 1 and layer 3, the permeability is same as 4 into 10 to the power minus 4 mm per second, while for the second layer it is 2 into 6 into 10 to the power minus 2 mm per second. So you see the K1, K2, K3 is mentioned for the upper, middle, and lower layer. Now K horizontal is uh, K horizontal is K1 H1 plus K2 H2 plus K3 H3 by H1 plus H2 plus H3. So H is considered as unit, so it is K1 plus K2 plus K3 upon 3. So K horizontal is calculated as 0.02066 mm per second. When we calculate K vertical, it is you considered as unit thickness. So 3 by 1 by K1 plus 1 by K2 plus 1 by K3, which is found to be 0.00597. Now with the question asked the ratio of KH by KV, when we calculate KH by KV, it found to be 33.3, 33.94. Okay, so the thickness is equal, no? So over here the thickness is assumed to be, over here the thickness is assumed to be unit thickness. Unit thickness. Unit thickness. Okay. So with this, the numerical problem kept for today is finished. Now I will move with some other concepts very quickly. Okay, and sum up the today class in some time. Okay. Okay, so I am talking about the soil compaction, the problematic geomaterial and the potential problems. So no, okay, the soil compaction, there must be some problems. So the talking about the type of geomaterial like soft clay. So soft clay has the low strength, high compressibility, large creep deformation, low permeability, whereas in silt it also have the very low strength and high compressibility. Permeability is also less. It is already discussed in this class only earlier that the coarse grained soil have the high permeability while the silt and clay have the very less permeability. When we talk about the organic soil is high compressibility, large creep deformation. Loose sand have low strength, high compressibility, high liquefaction potential, high permeability, high erodibility. While the expensive soil have large volume change, loess have large volume change, high collapsible potential. Talking about the type of geomaterial, moving ahead, when called uncontrolled field, when there is no control over the field, that it is kept over there in the given conditions. So their strength is also less and they are highly compressible. But in the dragged material is there, it have high water content, low strength, and high compressibility. Reclaimed field also have the higher water content, low strength, and high compressibility, while the recycled material have non-uniformity, high variability of properties. Solid waste have low strength, high compressibility, and non-uniformity, and the high degradation potential. The bio-based byproduct have the low strength and the high compressibility and the high degradation potential. Talking about the soil compaction. So compaction means to press closely together. In soil mechanics, it means the press the soil particle tightly together, expelling the air from the void spaces. Basically, that is the main purpose. Also, at some point of time afterwards, we also split water so that its void is filled with water. And then we do compaction till all the water voids also get pushed out so that the future consolidation is prevented. The consolidation also result in the reduction in the void ratio, but the consolidation and compaction are not same, right? Bilkul. The compaction is a instantaneous and the consolidation is a slow process. In consolidation takes place over the year. If it is a clay soil, the consolidation takes place maybe 100, 200, 500 years. Uh, for the primary consolidation only. The saturation is essential condition for the consolidation, which is not for the compaction. Right? For the compaction, the saturation is not essential condition, but for the consolidation, it is essential. Talking about the purpose of compaction, compaction increases the soil density and produces three important effects. First is an increase in the soil shear strength, decrease in the future settlement of soil directly. It and decreases permeability. The three effects are beneficial for the construction of the various types of earth structure, namely highway, airfield, earth dam, etc. The greater the compaction, the greater is the benefit. Compaction is cheap and effective way for improvement of the soil property. The conventional use of the roller and the plates are repeatedly apply the static pressure for the soil compaction and kneading action, vibration, and ground surface density geometry. These are used. You also have seen that in various highway construction when the soil is put over there, these type of rollers are usually used. and some water tanks is also present over there, which you use to drop the water. Then the roller is flown over there to achieve the optimum moisture content and the maximum dry density. The compaction is quantified by the dry unit weight, which can be computed in terms of the bulk unit weight. Mm, and the moisture content. In most cases, the dry soil can be best compacted if the certain amount of water is added to it. Yeah, as I already said, the water acts as a lubricant and soil particle to pack together. If, however, too much water is added, it results in the lesser density. Thus, for the given compaction effort, there is a particular moisture content at which the dry unit weight is greatest and compaction is best. This moisture content is called optimum moisture content, and associated dry unit weight is said to be maximum dry unit weight, right? So over there, when you draw the dry unit weight and moisture content graph, this type of graph is you get formed, and the optimum moisture content and maximum dry density is achieved at the maximum dry density. The moisture content is said to be the optimum moisture content. And in addition to that, when the compaction effect get increased, the optimum moisture content get reduced and the maximum dry density get increased. I think so this might be discussed okay over here only. In the soil compaction effect of effort, when we increase the compaction effort, you see that the moisture content get reduced, and as the blows 20 blows per layer, the maximum dry density is different, and optimum moisture content is different. But as the number of blows per layer get increased, the maximum dry density get reduced, we increase, while the optimum moisture content get reduced. It is shown from both the figure. Apart from that, for the effect of soil, you also see that the well graded soil have greater maximum dry density and lower moisture content as compared to the sandy, silty, or gap graded soils, right? Some of the instruments which is used in the soil compaction is like a smooth wheel roller employed. You have seen this on the various roadways construction. Smooth wheel rollers employ two of the three suits steel rollers. It is useful in the compacting the base courses and paving mixture. It is also used to provide the smooth finished grade. The smooth wheel roller provides comparative effort throughout its self weight. The second is a foot roller, consists of a drum as seen in the figure and attached projecting feet. The area of contact between the soil and the roller is less, causing the greater compacting pressure. It also provides kneading actions and is effective for compacting the fine-grained soil. Uh, Next one is a pneumatic roller consisting of a number of rubber tires as shown in the figure. Uh, Highly inflated and vary from a small roller to a very large and heavy. Most heavy pneumatic rollers are towed. Some smaller ones are self-propelled. Clay soil and the silty soils can be compacted effectively by this type of rollers. Also suitable for the granular soil containing the small amount of fines. Next one is a vibratory roller. Contains some kind of vibrating units that imparts an up and down vibration to the roller as it is pulled over the soil. Vibrating unit can supply the frequency of vibration at 1500 to 2000 cycles per minute depending on the compacting requirements. They are effective in compacting granular materials, particularly clean sands and gravels. Then the recommended type of compaction equipment is mentioned over here in the tabulated form. You can go across this. This is for your understanding, and many questions could be framed from this one. Like the question asked that for the rock fill, which type of roller is the first choice? So the vibratory roller. Yeah, what type of rollers are the correct options? So option A is vibratory, second is rubber tire, and third is impact roller. So you have to select A and B only. This type of option could be asked in the examinations. Moving ahead, lift thickness and the number of passes for the different compaction equipment is mentioned over here. You can go across these tables, the typical compaction requirement for different type of constructions like the road, smaller dam, large dam, embankment, etc. is also presented for your reference. Then that is only carried forward for the lift thickness, number of passes for the different compaction equipment. Then over here, that is only carried away. And now move to moving to the next section. Okay, so now we are talking about the application. So the conventional compaction has been used for the earthwork such as roads and dams, roads, embankment, dams, slopes, and parking lots and sport field. Advantage of this is the construction equipment is readily available. It is a well-established ground improvement method that has a long history and extensive knowledge in the industry. Um, Talking about the limitation, the depth improvement is limited, mainly used for fill and not for the in situ natural geomaterials. Geomaterials should be within the moisture content close to the optimum moisture content to be more effective. It is challenging to achieve uniform compaction of the geomaterial in the large area. This is already discussed that the compaction effort, high energy result in the increase in the maximum dry density and reduction in the moisture content. This is only presented from this figure, and same thing is presented over here. Now the recommended number of tests for the embankment. Subgrade base course is also mentioned over here. Now talking about the quality control and assurance, the quality control and assurance are important part of the conventional compaction because it often involves the large area of construction. Quality control typically indicates quality of the fill materials such as the type of gradation and the Atterberg limit, weight and type and weight of equipment, lift thickness, moisture content at the compaction, number of passes. Quality assurance is achieved through the flow field test after each lift compaction and or the completion of overall compactions. Field test for the quality assurance of compaction is mentioned over here, that what type of test could be conducted. Now moving to a non-destructive test, the apparatus is placed on the ground on the compacted fill and emits gamma rays through soil. Some of the gamma ray will be absorbed, others will reach to the detector. The soil unit weight is inversely proportional to the amount of radiation that reaches to the detector. The nuclear apparatus also determine the moisture content by emitting the alpha particles that bombarded by a beryllium target, causing beryllium to emit fast neutrons. The fast neutron that strike the hydrogen atom in water molecules lose velocity, resulting in the low velocity neutrons are the thermal neutrons. Based on the thermal neutron counts and the proper correlations, while moisture can be determined. The nuclear moisture density meter is shown over here. Similarly, the intelligent compaction is also a non-destructive technique in which a continuous construction technique with quality assurance and control process incorporated in the construction. This technique includes automatic measurement of the geomaterial property through pre-installed sensors on the machines and adjustment and the optimizations of the vibrations, amplitude, frequency, and or speed using the feedback control system by the machine operator to achieve the uniform compaction and desired target value. Suitability and application same as the conventional compaction rollers. Talking about the advantage and limitation, the IC method has a measurement and feedback system which helps the operator identify the weak spots for the further compaction or the treatment, and QC and avoid compaction. Currently, the equipment is more expensive than the conventional compaction equipment, so it requires managing and analyzing a significant amount of data. This method often requires the test strips for calibration of the target compaction value prior to the production component. So with this, the all the thing which need to be discussed for the today class is summed up. Now we move to the some of the questions very quickly. So first question is, which law govern the flow of water through the soil under the laminar condition? So options are Newton's law, Darcy law, Fick's law, Pascal law. If you are aware during this class, all one can answer in the very easily, that is the Darcy law. The second question said that the coefficient of permeability has a unit. This is also asked in the previous class as well, that is meter per second. Okay, option B, meter per second. Third is the Darcy law is valid for the flow in the soil through turbulent laminar transition or uniform. So this question is also there in the previous class as well. The option B, laminar flow, is the correct answer. Next is, which soil type has the highest permeability? So highest permeability is clay, gravel, silt, loam. So gravel is the correct answer. If you remember, I have said this class, previous class as well. Constant air permeability test is best suited for. We have solved the problem in this class also, that is the sand. Option C, for the coarse grained soil with higher permeability. Next question is, the variable head permeability test is recommended for. Okay, so we have performed the variable head permeability test for option number C, that is clay. Because over here, there the head varies, clay has less permeability also. The permeability and isotropy in stratified soil means the permeability is same in all direction and different in different vertical direction. So I think so option number B is the correct answer. Okay, anisotropy, not isotropy, right? Now next is, the seepage velocity is always equal to, or seepage velocity is always greater than the discharge velocity. Option C, right? Because discharge velocity by n, and n is less than 1, so seepage velocity is always greater than discharge velocity. In a flow, the net quantity of seepage is proportional to, okay, NF by ND hoga. This option is not written correctly, so option C may be mentioned correctly, that is NF by ND. Next is, the hydraulic gradient is defined as head loss per unit length. Option number B. Next is this question. Okay, I will give it to you. You solve by yourself. That is nothing but discharge velocity by n, 3 by 0.3. Answer will like that only. Option number B is the correct answer. Next one is also numerical problem. You solve by yourself. It will be there in the PDF. In a Darcy law, discharge velocity is directly proportional to V equal to KIA. So option C, V equal to KI. Okay, KK and hydraulic gradient K and I, right? Which factor reduces the permeability? So the permeability reduced due to increased viscosity reduces permeability. Option number B, right? And next question is, the hydraulic conductivity of soil at 20 degrees Celsius. This okay, we haven't discussed this yet today, so this question will be discussed in the next class. So with this, I will sum up the today class. I'm also not very well, so I also started class little early. So now I'm going to end the today class at this point of time only. Thank you everyone for joining. I hope you will solve some problem from the textbooks of the soil mechanics. Any book which you have with you, please solve the problem from those books, and see you in the next class. If you have any doubt, you can ask me, but please leave me today because I am not very confident to speak due to my health issue. So see you in the next class. If you have any doubt, any problem, you can ask in the start of class as well, or otherwise at any point of time. You may say that at the mid break of 5 minutes when I stop, you can say that I have this type of problem, so we can discuss over there as well. So thank you everyone for joining. I wish you a very happy weekend, and coming week is also coming Saturday, I think so it will be 16th of August. So okay, see you in the next class. Thank you everyone for joining.